Thank you, Suijan, for a very nice welcome. I'm really honored to be here. I'm delighted to be here. I'm a past collaborator with scientists from Tsinghua University. I met one of my old colleagues from Tsinghua from the Super Collider this evening, and I'm very glad to be here again tonight. Listening to the introduction, it seems like I've been around for a long time, and I've had a long career, but I'm still having fun. And one of the things, I have a few messages for tonight. One of the things I've come to learn in science is to try to work in science that will look at the universe, the physical world, the universe, in a different way. And when we see the universe in a different way, we will usually see a different universe. I have said this so many times that I find that people are quoting me in books. This book by Michio Kaku quoted me, "Every time we have looked at the sky in a new way, we have seen a new universe." And I've been lucky to work on a few things like that, like LIGO. And I'll give you a few examples. So that's the first lesson I want to talk about tonight. We think back to astronomy. Throughout human history, up until 1609, all astronomy was done with the naked eye. And we know that the aperture of the naked eye is very small. It cannot collect very much light, cannot see very far. But in 1609, Galileo used the telescope idea from Lippershey, and he used a lens about this size. It was a big advance, and what he saw was a different universe. Everything wasn't going around the Earth. The planets were going around the sun. It was a different universe, and it caused a great deal of controversy and arguments for which he paid a price. He also saw many interesting things in astronomy, and he started astronomy with refracting telescopes. But he looked at the universe in a different way, and he found a different universe. Another example is in about 1931, if you were in New York City and you wanted to make a telephone call to London, the telephone company would send your call by radio. And it was very noisy, a lot of static. So the telephone company asked this scientist, engineer, find out where all the static is, and perhaps we can make the calls cleaner. And he built this antenna with wheels from a Model T Ford, and he mapped the radio signals from the sky, and he found the radio from the sun, and he found radio waves from storms, electrical storms, but he found a source that didn't repeat with the rotation of the Earth, the 24-hour day. It was the sidereal day, the day that astronomers know. And he published a paper observing the brightest it was very bright also, very bright radio signal. Observed the brightest radio signal on a sidereal day, and he published this paper, Electrical Disturbances Apparently of Extraterrestrial Origin. He had seen a different universe. And interestingly, the optical astronomers in those days said it has to be wrong. Okay? They weren't ready to see a different universe, but he saw one. And we now know that it's Cygnus A, and what he was looking at was a system powered by a black hole and jets of gas and shock waves, radio sources, a different universe, something that hadn't been seen before. So that's another example, looking at the universe in a different way, seeing a different universe. Now, it was mentioned that I worked in high-energy physics on the superconducting super collider, and Tsinghua University was part of the team that I was part of. This is a picture of a detector that was to be built 32 meters long, 19 meters in diameter, a very big detector which wasn't built in the end because the United States didn't finish the project. But most of our colleagues went on to CERN, to the ATLAS and CMS detectors at CERN. And what we were going to look for, among many other things, was the Higgs particle, the particle responsible for mass in the Standard Model, and many other things. But this also was looking at the universe in a different way. And of course, many years later, after running the Hadron Collider, in one of the first runs, the Higgs particle was observed This is a very clean event where you have the quark annihilations producing a very clean signature of 4 muons, a beautiful event. And the Hadron Collider is coming on now with a higher energy and luminosity. And we will see that they will see not the Higgs that we were looking for, but we will see things that aren't expected, and I'm sure of it. They will see a different universe, even though finding the Higgs is a remarkable thing. But another point I want to make about that effort, unlike Galileo, unlike Karl Jansky, to do that kind of science took a very big collaboration. So the Atlas team, one of the two teams, has about 4,000 authors on the paper. And so the second theme in my talk is to do the work of seeing a new universe very often takes a very big investment in money and in intellectual power, very large collaborations, international collaborations, more and more. And the Large Hadron Collider is an example. So let's talk for a few minutes about what it takes to go from one scientist to many. So this is a picture of an astronomer painted by the Dutch master Vermeer. He's alone in his room. He's thinking about the universe. And that's the example of small science. He may make a very big discovery, but it's a small group, perhaps just him or him and a few assistants, some students. And let's look at another scientist also painted by Vermeer. If you study Vermeer, you'll see he does many paintings in this same room. This is a geographer. And imagine that these two scientists want to work together on some problem in perhaps astrogeology, how you form planets and do the astronomy to understand this. So they would have to work together, okay? Now Vermeer didn't paint this. This was done on the computer at Caltech. But putting them together in the picture is pretty easy. But imagine what it takes to have them work together and produce science together when they come from different fields. It's already a very difficult problem. So the first guy, the astronomer, he works alone as a researcher. He has not only the knowledge that you can learn in astronomy from books and papers, but he has what we call the tacit knowledge, the knowledge that comes from working in the field and talking to people and learning what people do and who's good and who's not so good and who gives correct results, the unwritten parts of the field. This is part of the expertise of being an astronomer or any individual scientist. He knows about the community and the shared history of the field. He's an expert, but in a narrowly defined field, in this case, astronomy. But with all this together, he can contribute to astronomy. He can write papers with new results. Now, if you put the two of them together, you have two different scientists with different histories. They have to learn to talk to each other. They have to interact. They have to learn just enough about each other's fields so they can talk to each other and make judgments together. And if that works, they can contribute to the joint science, the interdisciplinary science. That's already hard to do, although it's not that uncommon. Think about that Large Hadron Collider project with 4,000 scientists and engineers and business people, lawyers. I see one lawyer right here in the front row. Hi. And a project manager. What is a project manager? Might be a scientist, it might be an engineer, but it's someone who's an expert at making it all work together, but is not necessarily the most expert scientist or engineer in the group. Okay, so it becomes a very complex problem of sharing and respecting different expertise. It's essential, though, to modern large science. So when we train scientists, we train them to achieve science. We don't necessarily train them to work in groups or to make decisions or to respect people who make decisions. So an individual scientist is trained to live up there, to achieve the best science, to publish the best science. But if you're going to do a CERN experiment to look for the Higgs particle with 4,000 scientists, you have to have a team that can do all of these. Work together and share the work. Okay? Good. work together and share the work, affiliation, and also respect decisions. Even when you disagree with the decisions, make the decisions of the leadership successful. That's a skill. And they don't teach you that in graduate school. So with that introduction about what it takes to put a large team together, let me give you two examples